Welcome. In this video, we are going to talk about the inner working of decompression algorithms. We'll see how those algorithms track gas absorbed and expelled by tissues, how the decompression ceiling is calculated, what happens in repetitive dives, and some considerations about those algorithms. Warning: this video is for educational purposes only. The dive profiles shown in here were made entirely with theoretical models, most of the time known to be harmful to divers. Do not use these profiles in real dives. There are several decompression algorithms models, like Haldane, ZHL, DCIEM, RGBM, VPM, and many more. They can be divided into the following categories: gas content models and bubbles models. In this video, we will focus on the gas content model, especially Haldane model and ZHL. In gas model content, the decompression profile is calculated by tracking the amount of inert gas absorbed by the tissue and how much gas can leave the tissue without causing any decompression sickness. When our body exchanges gas with the environment, the tissues can be in three states: saturated, on-gassing, or off-gassing. In the saturated state, the pressure of inert gas within the tissue is the same as the environment. So, there is no gas coming in or out of the tissue. If you have been in the same altitude for the past 48 hours, your tissues are probably in a saturated state. In the on-gassing state, the pressure of ambient is greater than tissue pressure. In this state, gas will flow inside the tissue. In the off-gassing state, the pressure of ambient is lower than tissue pressure. In this state, gas will flow outside of the tissue. Keep in mind that this is a major simplification of how inert gas is handled by the body. Remember that we are ignoring the partial pressure of CO2, partial pressure of water vapor, and temperature. With those considerations, the gas exchange within the tissue can be tracked by the following equation, where the rate of change of tissue gas is directly proportional to the difference of a tissue and ambient pressure. The rate of change is also proportional to a constant K that depends on the tissue. If we consider that the ambient pressure is constant, we can solve this differential equation for the tissue pressure. This is known as Haldane equation. On the other hand, if we consider that the ambient pressure varies linearly in time with rate r, we can solve this equation for tissue pressure. This equation is known as Schreiner equation. And the constant r have dimensional unit of pressure per time. With those two equations, we can compute the amount of gas that a certain tissue K will absorb or expel if we descend to a certain depth with a descent rate r, or if we stay at a certain depth for a time t. We can use the follow graph to show how a single tissue absorbs inert gas, or inert gas is eliminated by the tissue, depending on the depth pressure. Throughout this video, the pressure will be shown in bar. The surface has 1 bar at sea level. Each meter of salt water adds up roughly 1 bar of pressure. In this example, the maximum pressure is 2 bar or 10 meters. Note that we are tracking inert gas within the tissue. In this case, air with 79% of nitrogen. As time passes, our tissues will intake gas until saturation. At this stage, the inert gas pressure within the tissue is equal to inert gas pressure in ambient. If gas pressure within the tissue is lower than inert gas pressure in ambient, the tissue will be in the on-gassing state. If gas pressure within the tissue is greater than inert gas pressure in ambient, the tissue will be in the off-gassing state. But what about that constant K? A convenient way to define a tissue is using its half-time. A tissue half-time is the amount that a tissue takes to get 50% saturated. For instance, a 4-minute half-time tissue will take 4 minutes to get from 0 to 50% saturation. The tissue will take another 4 minutes to saturate 50% more, going from 50% to 75%, and so on and so forth. Haldane and Schreiner can be rewritten in terms of half-time, where this is Haldane equation, and this is Schreiner. Notice that with only the tissue half-time, we can calculate its gas absorption profile. With those two equations in hand, John Scott Haldane in 1907 created the first decompression table. First, Haldane defined 5 tissues with half-times that goes from 5 to 75 minutes. Those values of half-time are somehow arbitrarily defined in all gas content models. The amount of half-time and its duration are chosen to fit the data available. Okay, so far so good. Let's see an example for a 50 meters dive or 6 bar of pressure for 40 minutes. Haldane could use Schreiner equation to track the amount of gas absorbed by the tissue in a descent from surface to bottom at a 1 bar per minute rate. Remember that we are tracking inert gas. Air has 79% of nitrogen, so the saturation pressure for 50 meter will be 4.74 bar. Then, the amount of gas intake could be measured with Haldane equation for the amount of time the diver spent underwater. In this example, the diver stayed for 40 minutes. Finally, Schreiner equation can be used to track the amount of gas that the diver lost if he goes back to surface. If you came here with any dive experience whatsoever, you know that this profile will be problematic. How much gas can a tissue lose before decompression sickness? Haldane hypothesis was that a tissue could hold a ratio of 2:1 of inert gas compared to ambient pressure. Now we can track the gas intake and maximum pressure allowed for each half-time every time. Using Haldane hypothesis, we can see not only the gas intake by the tissue, but also the maximum pressure allowed. We can see that the maximum allowed pressure is 2.36 bar or 13.6 meters. As the diver approaches 13.6 meter, he will outtake gas, and a new ceiling will form. And the profile will go on until surface is reached. We can use a more traditional way to show this dive profile. This new graph shows the profile of the dive in terms of time and depth pressure. We can see the gas intake as the diver descent and stay at his 40 minutes bottom time. The diver will ascend, never going shallower than the max ceiling allows. If at any time the dive gets closer to a ceiling, he will slow down the ascent rate to allow degassing of the tissue. If we noticed, this profile is quite hard to follow. As the ascent rate gets slower and slower, it becomes very difficult for a diver to track which depth he should be throughout time. This is true, especially as the diver gets closer to surface. Near the end of the profile, the depths get impossible shallow to precise follow, more so in rough seas. That is why we use decompression stops. A decompression stop is a standard depth in each the diver must wait until enough gas is eliminated. After enough gas has flowed out, the diver can ascend to the next decompression stop. And so on, until the surface is reached. Each decompression stop is by convention 3 meters apart or 10 feet. The last stop, the one closer to surface, usually has a depth of 6 meters, which is the maximum operational depth for pure oxygen. But since Haldane models do not use oxygen to accelerate the decompression, we will use 3 meters as the last stop in this video. In our example using Haldane model, the profile will start the same until the 2.2 bar or 12 meters is reached. At this point, the diver can no longer ascend to the next decompression stop and must stay until decompression is cleared to next stop. The next stop happens at 1.9 bar or 9 meters deep. Once more, the diver stays until the next standard ceiling is reachable. We follow the same logic until the divers finally reach surface. To surface means that at least all the tissue ceiling are just below surface pressure. In this case, tissue 4 has a ceiling of about 1 bar of pressure. This do not mean that the tissues are saturated to surface pressure. We can compare the gas profile of a diver that just finished the 50 meters dive with the gas profile of a diver who is saturated at sea level. They are very different, and we can see that even gas absorbed by the fastest tissue is higher than atmospheric pressure in this case. The tissue with most gas absorbed is even higher. This will incur in penalties for repetitive dives. We can compare the repetitive dive for our example with a fresh diver saturated at sea level. Let's make both divers repeat the same profile. The diver saturated at sea level ends up with the same dive profile and the gas absorption as the first diver. But when the diver, who already made the 50 meters dive, repeat it, his decompression profile will be much longer. We can see here the time length difference. Note that all decompression stops have increased in duration. So repetitive dives will always incur in longer decompression obligation, or, for recreational dives, in shallower and shorter dives. Those obligations will get after each repetitive dive longer and longer. That is because the slower tissue will have higher and higher amount of dissolved gas. Of course, the more time the diver waits for the second dive, the lower the penalties will be. That is because the diver will expel gas until return to saturation with sea level. And this is how Haldane created the first dive tables. His model is arguably the most important breakthrough in hyperbaric science. But the ratio of 2-to-1 was too conservative for shallow dives and not conservative enough for deep dives. Haldane knew that, and throughout his career he experimented and adjusted this ratio for different tissues half-time, going from a ratio of 3.4-to-1 up to 1.1-to-1. He also increased the number of half-time tissues. In 1959, Professor Albert Alois Ballman started the research that will lead to what is probably the most used dive decompression algorithm so far, the ZHL16. The research began when deep diver Hannes Keller started to experiment with mixed gas dives. Professor Buhlmann got involved, and Keller did dives from 120 meters to 220 meters deep. With all those data, Professor Buhlmann developed the ZHL16 algorithm, where ZH stands for Zurich, L stands for limits, and 16 for the number of tissues. For ZHL, the on-gassing and off-gassing in ZHL works pretty much the same way as in Haldane algorithm. The main difference from Haldane and ZHL is the number of tissues that went from 5 minutes up to a little over 11 hours. The second difference is how the maximum sealing is calculated. From previous work, Professor Buhlmann knew that there is a linear relation between the inert gas pressure and the ambient and maximum sealing allowed for each tissue. Professor Buhlmann expressed this linearity in the form of A and B coefficients for each tissue. Different from previous work, his coefficients are a relation of tissue gas pressure and maximum allowed ambient pressure, or in this case, our sealing. I could not find any reference of how Professor Buhlmann has derived the A and B coefficients, but apparently he did some curve fitting to his data to get to those coefficients. The coefficients are calculated as shown. We can see that those coefficients only depend upon the half-time of a tissue. Okay, let's crunch some numbers. We will simulate a dive with ZHL for a single tissue saturated at surface. This tissue has half-time of 5 minutes. This will be a 50 meters dive with descent rate of 2.2 bar per minute or 12 meters per minute. We calculate the A and B coefficients. The coefficient for 5 minutes half-time will be around 1.16 bar. The B coefficient for 5 minutes half-time will be around 0.55. We start descent to 50 meters. We can calculate the time that will take for this. In this case, about 2 minutes. The gas intake is calculated by Schreiner equation. Remember that we are tracking inert gas. So, for a 79% of nitrogen mixture, the inert gas pressure in the lungs of the diver will be 0.79 bar. If we plug the values we already have, we will end up with a value of 1.35 bar. Let's ascend. The diver will stay at this depth for 40 minutes. We use Haldane equation to calculate the total gas absorbed by the tissue. Once more, at 6 bar of pressure, the inert gas pressure in the lungs for a 79% nitrogen mixture will be 4.74 bar. Now the tissue has a pressure of about 4.72 bar, that is almost the saturation pressure of the tissue. So far, this is exactly the same as Haldane method. As the diver starts ascending, we need to calculate the next sealing. Using A and B coefficient, we get the value of 1.98 bar for the sealing, or 9.8 meters. We can show in the graph that 9.8 meters is between 12 and 9 meter deco stop. 9 meter deco stop is to shallow, so the next standard deco stop for this sealing is 2.2 bar, or 12 meters deep. The ascent rate is usually slower than the descent rate, for safety reasons. In this case, we are using an ascent rate of 1.0 bar per minute or 10 meters per minute. As diver ascends to this deco stop, he starts to expel gas, according to Schreiner equation. The new sealing is calculated each step of way up. The new sealing is calculated. The sealing value is about 1.58 bar or 5.8 meters. This means that the next standard deco stop will be 6 meters. Take a note that we didn't need to stop at the 12 meters deco stop, nor the 9 meters deco stop. That is because the diver degassed enough to go to 6 meters ceiling. The diver can ascend to next deco stop at 6 meters or 1.6 bar. Although the diver has degassed when he reaches the deco stop, when we calculate the ceiling once more, we can see that the diver may still wait in the 6 meter stop. The 3 meters deco stop is still too shallow for the diver. The diver will stay at this depth until he can reach the next deco stop. To find the amount of time the diver will stay in this depth, we can wait at this depth for a standard amount of time. Usually, the dive computers stay at a deco stop for periods of time no less than a minute. In this case, we degassed for about a minute in the deco stop. After a minute in this depth, the diver can go to next deco stop at 3 meters deep. The process continues until surface is reached. To see a dive profile with ZHL16, we just need to repeat this whole process for all 16 tissues until the diver reaches surface. And we will have our dive profile. Okay. Even though we are not using the best coefficients for ZHL, we still may consider it as a golden standard for a safe dive. When we compare Haldane model to ZHL, we see that Haldane is too conservative for fast tissues and not conservative enough for slower tissues. But what does it mean? We can compare a 40 meters diver for 10 minutes between Haldane and ZHL. We start both dives. The first thing we can notice is that ZHL predicts no need for decompression and Haldane predict 2 decompression stops. We can see that Haldane total length is greater than ZHL. In this dive profile, with fast bottom time, the limiting factor will be faster tissues. If we compare the ceilings for Haldane and ZHL, we see that the fast tissue in Haldane has a ceiling greater than the ceiling for ZHL. On the other hand, the slower tissue of Haldane and ZHL have a ceiling comparable to each other. Since ZHL is our standard, this means that Haldane is too conservative for dives bounded by fast tissues. Now, if we compare a 40 meters dive for 40 minutes. In this longer dive, the slower tissue will intake more gas and will have a greater impact on the overall decompression time. We start both dives. We can notice that ZHL predicts a longer decompression time when compared to Haldane model. ZHL demands not only longer decompression time, but also deeper stops. Comparing the gas intake between both profiles, we see that the maximum ceiling for faster tissue is still greater than ZHL, meaning that it is more conservative. But the ceiling for the 75 minutes tissue in Haldane is far below the ceiling for the 77 minutes tissue in ZHL, meaning that this slow tissue is not conservative enough. We can compare the decompression demand for ZHL and Haldane models for several depth and bottom times. The depths varies from 25 to 50 meters deep. We can see that for a 10 minutes bottom time, Haldane is always more conservative than ZHL, predicting longer decompression time. ZHL only required decompression for dives 40 meters or below. Decompression for those fast bottom times, as stated previously, are bounded by fast tissues. For a 20 minutes bottom time, Haldane is more conservative than ZHL only for dives shallower than about 43 meters. We can see that the effects of slower tissues start to kick in. Finally, for a 40 minutes dive, where the slow tissues start to dominate the decompression time, ZHL is always more conservative than Haldane. That's it for today. We hope you have enjoyed and learned something useful. Next video we will address the usage of mixed gas and multiple mixtures in a dive. See you next time, and safe dives for us all.